Hi there, we'll continue our discussion, actually our computation for the fourth sample problem, and we are dealing with a 3D state, 3D state of stress. Okay, so what if we have this actual, these normal stresses that's acting in all the three directions, and let's say this is our x, this is our y, and this is our z. Now it's also possible to have shear stresses as well. Shear stresses in both shear xy, shear yz, and shear xz. So it's also possible, but for now I just select this sample problem because this will be simpler in terms of the computations. The some of the terms are just zero. So actually, the method of the book, it uses something like a plane. The method used for plane stress, and that's why right here it says that plane stress shown. Okay, so although it works as well, I just wanted to use this method of using the characteristic equations. This cubic equations and solving the stress invariants. So in order to check whether this also works, and it actually does. Okay, so just to have a review, this is our 3D state of stress, and the characteristic equation is this. And when I say characteristic equations, that's where we are going to obtain the value of the principal stresses sigma 1, sigma 2, and sigma 3. So right here, this is a cubic equation, so the roots, we are going to have three roots, and that three roots corresponds to sigma 1, sigma 2, and sigma 3. But we need to solve for this I sub 1, I sub 2, and I sub 3. These are constants, and these are the stress invariants, and we need to solve that. And for the first stress invariance, this is just the summation of the normal stresses, and for the second stress invariance, are just the product of the stresses here, and we have the square of the shear stresses. And since we don't have shear, then this is just 0, and the value is negative 350 ksi. Actually, this is ksi. Sorry, this should be ksi squared because that's a product. And for the third stress invariance, this is computed using a determinant. And when dealing with determinants, we can just input that in the calculator so that we can solve it in a much simpler way, or in a much faster way. Okay, so here's the arrangements of the determinants, and we just substitute all the values right here: 10, 0, 0, 0, 0, and this is 15, 0, 0, and negative 20. Okay, so how do we do that in the calculator? Okay, so I'm using a Casio FX991 ES, which is just typical for engineering classes. And to solve for the determinants, right? So let's say you turn on the calculator and you press this button, this mode button. So right here, there's actually a selection if what's going to be the mode. Is it the computation mode? Is it the statistics modes or equation modes? Or right here we have a matrix mode. So this is number 6. So if we select 6, that's going to be matrix. Okay, so let's press the button 6 because that's matrix, and it asks a question here, matrix, that's a question mark, and we are going to input a data. So that's matrix A, so we can input in A, in B, or C, because sometimes it's also possible to add matrix or multiply matrix. But for us here, we only need one set of data, and let's say we are going to store this data, this matrix, in A. So let's press 1. Okay, so it says here, what's the size of the matrix? Is it a 3 by 3, or is it whatever? So since this is a 3 by 3 matrix, then we are going to select 1, and it enters us into this view wherein we can input the values. Alright, so let's input the data. So we are going to start from 10, and once um, okay, let me press this then. So 1 0, and then okay, so this is 1 0. So let's press 10 and equals. So that um, that turns us to the right, and the right value is 0, and then another is 0. Just press equal, and then the second row, this is 0, 15, and 0, and the third row is 0, 0, and negative 20. Okay, so uh, that's the data here in matrix A. So actually, if you press equals, then there's nothing gonna happen, and we need to press the AC so that we can get back to the main menu. Okay, so of course it might be we feel like if we press the AC, we are going to lose the data right here, but it's not. Okay, so it's stored in A. Okay, so let's press the AC, and because we're still in the matrix mode, okay, and you notice right here we have in these numbers we have here like the if we press the shift button here is it says stat, this is complex numbers, this is base, this is matrix, this is vector. So we are going to enter the matrix. Okay, so let's press shift 4, and it the selection right here we have the number 7. That's the determinants, because we are going to take the determinant of the matrix, actually matrix A. So let's press 7, and you notice right here it says determinant of what. So again, we press shift 4, and we press 3 because that's where we store the data, and that's it. That means that we are going to take the determinant of the matrix A because that's where we store the data. Okay, so it says here we have a value of negative 3000, and this is actually KSI cube. If you check the units, it's gonna be cube. Okay, now since we have the stress invariance, then we can now solve for the roots of the characteristic equation. Okay, so we have sigma, let's say sigma p cube minus the value of I sub 1, so we have 5, minus 5, this is sigma p squared, plus the value of I sub 2, this is negative 350. Right, negative this negative 350, and this is sigma p, okay, minus I sub 3. So what is I sub 3? This is minus 3000, and this is equal to 0. Okay, so how do we solve for the roots? We can just simply go to the calculator. So again, let's press the mode, and right here we have this we have a selection for the equations, and this is number 5. Okay, so in this function, whatever equation we have, like we have a quadratic equations or cubic equations, we can solve for the roots. So in this selection, you would see here that we have a linear equation with x and y only, or we can have a linear equation of x, y, and z. And for the third selection, for the number 3, this is a quadratic equation, and for the fourth one, this is a cubic equation. Okay, so that's what we are going to select. But take note that this cubic equation, you will notice that a constant right here, that's the constant a, b, c, and d, and the term right here, we have a positive term, so we have to be really careful about the signs right here. So I'd like to write in terms of the letters right here. So what's gonna be the constant in this sigma? In this cubic term, and also take note all the all the values or all the terms are in the left hand side, and the right hand side must be 0. Okay, so if we write the equation, the right hand side must be the same as the ones in our calculators. Okay, so this one for letter A, that's the coefficient. This is just 1. And for letter B, just take note, this is plus and this is minus. So this must be negative 5, right? So plus, or let's just write it here, plus minus 5. And for letter C, because this is plus, then this will be negative 350. And for letter D, since this is negative, because that's our characteristic equation, that's negative, or minus negative, so negative times negative, that's gonna be positive. Okay, so we are going to input this this value in our calculator. So just press 4. So right here we have a space wherein we can input the coefficients. So for letter A, this is 1. For letter B, this is negative 5. And for letter C, this is negative 350. And by the way, this is just the same as how we input in our matrix. Once you input the values, then you just have to press the equal sign. Okay, and the last one, this is 3000. Okay, so that's so far that's the coefficients of our characteristic equations. And once we press the equal, okay, if we press the equal, we the calculator will give us one root value. Okay, so that's in terms of right here it says x1. Okay, so for our first root value is, let's just write x1, although it's this x value or this x symbol actually corresponds to the principal stresses, but sometimes it's not in order, like we have the sigma 1, sigma 2, and sigma 3. So let's just write x sub 1 and say here negative 20, and for x sub 2, by the way, I just press the equal button, so this is 15, and another x sub 3 value is 10. Okay, so which one is the greatest? So this is gonna be our sigma 1, and this is gonna be our sigma 2, and this is going to be our sigma 3. Okay, so with that, I think we can now draw. That's right here. We can now or drawing now the what else? Drawing now the Morse circle. Okay, so that's our next step, because we now have the principal stresses. And for our Morse circle, we have a negative 20, so it's more on the compression side. And so let's say this is our 10. This is maybe this is 10 or 5, 10, 15 probably. And here 5, 10, 15, 20. So this is negative 20. The other one is 10, and the other one is 15, right? So if we draw the circle right here, so this is 1 point. This is our sigma 1, right? Sigma 1, and this is our sigma 2, and here is our sigma 3. So we'll draw one circle right here, and we'll draw another circle and the third circle, the out of plane circle, that's gonna be this one. Okay, so let's label this. This is sigma 1 and sigma 2, and this is 15 and this is 10. So that correspond to the xy. Xy stresses, plane stress. Right, so let's write it here. This is transformation in xy plane, and this one is 10 and negative 20, so that's xz plane. Right, so let's write it here, transformation in the xz plane, and the largest circle, this is 15 and negative 20, so 15 and negative 20, this is compression. So this is transformation in the YZ plane. Okay, so right here we can actually obtain the maximum shear in this plane and in this plane right here, but the absolute shear, absolute maximum shear. Okay, so we just denote that shear absolute because that corresponds to the maximum or the radius of the maximum circle, and the maximum circle is this, which is just equal to 15. So this is 15 minus 20. So 15 minus negative 20 divided by 2. And if we do this, 15, by the way, we have to go back to the computation mode. So let's press 1. And 15 minus 20 divided by 2. And this is 17.5 KSI. Okay, so that's all for this 3D state. It's also possible, as I've mentioned, that it's also possible to use this method when we have shear stresses in all the three directions. So you just have to use this. The first step is simply to solve for the stress invariance, because once we have the stress invariance, then we can solve for the characteristic equations. And you just have to follow through the formulas right here, except that for the third stress invariance, we are using a calculator so that we can do it faster. We can find the determinants, and we just have to input that. And after that, once you have the stress invariance, then we can solve for the roots of the equations by using the calculator as well, using the equation mode. So we just have to take note for this sign, the positive, positive, and positive right here, because that's the default arrangement in our calculator. So once you mess with the signs, then you would get erroneous values. Okay, so that's why I write here A is equal to 1, B, C, and D, because that's what I'm going to input in my calculator. So once I have that, then we can find the roots, and the roots are given directly by the calculator, and we just have to arrange the values whichever is the biggest. Okay, and after that we can draw the Mohr circle. And since we have three principal stresses, then we know that we have three circles right here, and the maximum shear occurs at the radius of the maximum circle. Okay, so that's it. So I guess that's all for this stress transformation topics, or we still have to do one more sample problem about the I think application, since we still have time. All right. Okay, so for our next sample problem, this one is taken again in the textbook by Peitel and Acusalas, and this is sample 8.10. Now, I chose this sample problem because this is kind of different, because instead of finding the maximum stresses, this one is actually asking us to find not the stress, but rather the torque right here. So it's like a different view of computations. So that's why I think we need to go through this, or we need to have this sample problem, so that we can have a feel of what the solution will look like if we have this type of problem. Okay, so the problem says that the thin-walled cylindrical pressure vessel, that's a actually that's a special topic in structural materials when dealing with stresses in cylindrical pressure vessels. It says here with closed ends has a mean radius of 450 mm and a wall thickness of 10 mm. Okay, so this is the thickness, that's 10 mm, and a radius, a mean radius. When I say mean radius, that means that it's somewhere here. That's 450 mm, and it says here that in addition to an internal pressure of 2 megapascals, the vessel carries a torque as shown. So inside there are stresses, and as I've said, this is actually a special topic in the strength of materials, to compute for the stresses. So what I did right here is to just simply skip all those formulas for the pressure vessels and obtain this, or give you this 3D or plane stress, plane plane stress, plane, what do you call that, planar state of stress. Okay, so we have a sigma x, which is 45 megapascals, and along the sigma y, and this is 90 megapascals. And actually, if we are going to look this into detail, this is curved, but again, this is an infinitesimal value, so we can just simply represent that by a perfect cube right here. Okay, so we are asked to determine the largest allowable value of torque if the working shear stress is uh, working shear stress is 50 megapascals. So that means that if we draw the Mohr circle, then the largest circle would be, or the largest circle would correspond to this 50 megapascals. All right, and you would notice here that this is just a plane stress because we only have sigma x and sigma y, and the sigma z, this is actually 0. Okay, so if this is 0, we can plot actually uh, the largest circle. Okay, so for the solution, so the first step is to draw the Mohr circle corresponding to a shear stress, allowable, or the working shear stress of 50 megapascals. Okay, so again, this is not this. This is something like the absolute, or the absolute shear. So if we draw the circle, it will look something like this. So since this is 50, and we know that the 50 is just simply the radius, and we know that this sigma z is 0, then that point is right here. I mean, one of the point for the principal stress is a 0, so it's somewhere here. So we count 50, 1, 2, 3, 4, 5. So let's say this is 50, because that's going to be the radius, and another 50 right here. 1, 2, 3, 4, 5. Right, so that's going to be our one of our principal stresses. So right here, 1, 2, 3, 4, 5, that's going to be our absolute shear, or our allowable, or working shear stress. Okay, so this is shear here is absolute, which is equal to 50. Okay, so take note, this Mohr circle is not the Mohr circle corresponding to the xy, but rather this is an out of plane. Okay, so this is actually 0, and I think this is the xz plane. Okay, if I'm not mistaken, but what I'm sure about is this is not the xy plane. Okay, so the next step is determine the radius for the xy plane. So this is the xy plane. Let's write here x, and this is y, and also the average, and also the average stress. Okay, so for the average stress, we can compute this because we have sigma x and sigma y. So let's write sigma x plus sigma y divided by 2, and we have 45 and 90. So this is 45 plus 90 divided by 2, and what we get here is 67.5. Okay, so that's if we plot it here, if this is our 50, then 50 right here would be our 60, and then this is 70, so somewhere right here. So this is the the sigma average for the xy plane. Okay, so sigma average for the xy plane, and we know graphically, I mean in this graph, we know that this is going to be the radius. So what is this radius in terms of equation? We know that this is 100, right? This is 100 minus I mean from this point to that point, that is 100, and minus this, that's going to be our radius. Okay, so radius for the xy, okay, I just write it here, for the xy plane, radius for the xy is 100 minus the value of this one, of this average shear stress. This is 67.5, and we get a value of 32.5. Okay, so it's gonna be we can now solve for the minimum. Now for the minimum, we have simply the average minus r. So this is 67.5 minus the 32.5. Let's compute this. 67.5 minus 32.5. This is 35. Okay, so 10, 20, 30. Okay, so it's some. I think this is gonna be somewhere here. Okay, so this is the transformation along the xy plane. Okay, so this is it, and there's going to be another right here. But since we have this stresses in the xy plane only, and we are asked to find the maximum shear right here. So what's going to be the maximum shear right here for the xy plane? So to compute that, okay, so to compute the maximum shear, we will use the radius equation. Okay, why? Because in the radius equation, we know that r squared is equal to the sigma x minus sigma y all over 2 squared minus, or actually plus, the square of the shear. So we have the values of r, we have the value of r, and we have these values, and we can solve for the shear. Okay, so for the shear stress, this is just simply square root of r squared minus sigma x minus sigma y all over 2 squared, and if you substitute all the values of the equations, what we get is 23.45 megapascals. Okay, so here's our shear stress. So once we have the shear stress, then we can actually solve for the torque, because the torque is just simply the shear stress is simply dr all over j. So we have this, we have the j, we can solve for the j, and if we have the shear stress, then we can solve for the torque. Okay, so let's write it here. Solve first for the polar moment of inertia. So the polar moment of inertia is actually a resistance, or something like a resistance to rotation. And if this is our cylinder, and take note of the word thin-walled cylinder, and we are considering this area right here. And for this area, we have like the mean radius, and that's going to be in the center, or in the midpoint of this outermost diameter and the innermost diameter. That's going to be our R, right? And recall that J, or moment of inertia, or either polar, moment of inertia or polar moment of inertia, is just simply the uh, area times the square of the moment arm. Okay, so which area, or what area are we going to consider? And that's actually the area of this circle, except that since this is a thin-walled cylinder, then the area is just simply um, the 2 pi r. Okay, so 2 pi r. Okay, 2 pi r, that's the circumference. 2 pi r times the thickness. So it's like if you are going to transform this into something like this. So the length value is 2 pi r, and the thickness is this. Okay, so that's how it works for a thin-walled cylinder. And if this is our area, then if we multiply this to the r squared, then our J is equal to 2 pi r cubed times t. So that's going to be our working equation. And if you substitute all the values, of course the radius is referring to the mean radius, is 5.7 26 times 10 to the negative 3 meter to the fourth. Okay, now that we have this, then we can now solve for the torque. And we are going to solve that using the torsional stress equation, which is TRO over J, and T is simply the shear stress times J, this is the shear XY, divided by R. Okay, so if we substitute all the values, what we get here is the shear XY. This is 23,450 in terms of kilonewtons per meter squared. This one is megapascals, but I'm going to convert that to kPa, times the J. So the J is 5.726 times 10 to the negative 3 meter to the fourth. And the radius is, in terms of meter, this is 50 meters. And therefore, the torque would just be limited to 298 kilonewton meter. Okay, so that's one of the application of this Morse circle. And there's a lot more variation out there. I mean, a lot more variations for the problems that, for example, given the stresses and the torque, then we are going to find the diameter. So that's also possible. That's another approach or another perspective of designing. So just recall that in our lecture in structures engineering, that we have something like an analysis problem, and we have a design problem, right? And we classify those types of problems, like when we say analysis, given the geometry, find the loads. And in a design problem, it's like given the loads, then you have to find the size or the geometry. Okay, so that's a different attack in solving, but the working principle should be the same. Okay, so I guess that's all for this stress transformation topics, although it would be best if we still have another sample problem about finding the size given the stresses and the torques or the internal forces. Then we are going to find the size. But anyway, I think that's enough, and in the next video we'll move on really to the topic on fatigue loadings. Okay, so see you in the next video.